So, retrieval roulette, pause, get answering. Okay, so here's our answers. No, wait, hold on. That's better. I had cut out one of them a little bit. That first one, how is beta written in a nuclear decay equation? So the wee beta symbol, 0 at the top and -1 at the bottom. Or you can write E for electron and then 0 at the top and -1 at the bottom. The rest of them there, I think, are okay. So again, once you get that paused and marked, then let's get on with today's stuff. So after using the equation for weight all year, we're finally getting to it in the notes. Now, see, in everyday life, mass and weight do tend to be used interchangeably, but in physics we need to be super careful that we don't mix them up or use one in place of the other. If you're asked for the definition of one of them, make sure that you give the definitions that we have down here, or just be super careful in calculations like if it's asking for a mass and you have to find that mass through finding the weight first of all, then just be super careful that you do that, because it's such an easy wee mistake to do. So this shouldn't be too long a video here today, because we know the equation already, but I just want to go through the notes. Right, so if you're asked what mass is, it's really a measure of the amount of matter in an object. It's always the same. We don't mean that like every single object has the exact same mass, obviously, but if I have my calculator here with a mass of 0.1 kilograms, if I take that to the moon, it's still going to have a mass of 0.1 kilograms, whereas its weight will change. So that's what we mean by that. Measured in kilograms, obviously it can be measured in grams and things as well, but 99% of the time in physics we will have mass in kilograms. And it's scalar, so remember what that means. Scalars don't have directions. Weight is a force, so that means it's measured in newtons, and it is due to the pull of gravity on the object. So any object that has a mass, if it's in a gravitational field, it's going to have a weight as well. So that's what I was meaning whenever I was saying like there with my calculator. Its mass, if I take this calculator to the moon, its mass is going to stay the same, but its weight will be different because the gravitational pull is less on the moon. So if I was to set it on like scales that tell you the weight, it would be different, but its mass is going to be the same. So yeah, it's going to change depending on the pull of gravity. Because it's a force, it's measured in newtons, and it's a vector because it's a force, so the direction matters. Now, if we were in school, we would do this little practical. Do you know what? You did this last year actually in year 10. So what we would do is we would take different objects, it's like a calculator, and we would set it on a balance and measure its mass, and then we would use a Newton meter or a spring balance and use that, like hang it from it. Do you remember those wee things that you used? Hang it from that, and that'll tell us its weight in newtons. And the whole point of that was so that we would eventually notice that whenever we divided all our weights here by masses, we should have got about 10 for all of them, right? I'm not going to like put fake results in, but this is the important point, that we would have eventually reached this point where, and it wouldn't have been exact, there would have been like it would have been like 9.5 or 10.2 or whatever, but roughly this here column would have always ended up being 10, and then that would have been us discovering the relationship between mass and weight. So over on to 195 then for me please, the conclusion that we would have got from that. Either just looked at how I wrote it last year. I wrote weight divided by mass gives us a constant value, which is 10. This year I've written it slightly differently. I've said on Earth weight is equal to mass in kilograms multiplied by 10. Now get that in. The equation that we need to know and use, which I think we already know, all of us already, is weight equals mass multiplied by gravity. So W in this equation is weight in newtons, M is mass in kilograms. You can't put mass in grams into this equation, it will not work. And then G is the gravitational field strength. On Earth at GCSE we use the value of 10 for that. The units are newtons per kilogram, because to get this we are dividing a weight in newtons by a mass in kilograms. So that's why it's newtons per kilogram. So on Earth it's 10. You're expected to know that value You might find that you get questions where like an object is on the moon or something like that. They don't expect you to know the gravitational field strength of anywhere else apart from the Earth. They'll tell you it if the question is set somewhere else. If they don't mention where it is, you'll just have to assume it's on Earth. Okay. So the value of G is roughly the same everywhere on the Earth's surface, but the further you move away from the Earth, the smaller. Change that for me, please. G becomes. So, like, yeah, as you were to rise higher and higher and higher through the Earth's atmosphere, then gravity is going to get less and less and less and less. Okay. Now, wee bit of a note down at the bottom here. The moon is smaller than the Earth, so it's going to have a smaller gravitational field. The general rule is that the bigger the mass of an object, the bigger the gravitational field it will have acting around it. So the moon is smaller than the Earth, so pulls objects towards it less strongly. On the moon, it's about 1.6 newtons per kilogram, as opposed to Earth here, where it's 10 newtons per kilogram. So this means that you'll weigh less on the moon than on Earth, but it doesn't mean that you are actually any different. So if you were to stand on a set of scales that give you your weight here, stand on a set of scales that would give you your weight on the moon, they'd be very different, but your mass would be the same on both. Right, over on to 196 then. See this wee bit here? It's really just showing you that W equals mg is just like a special version of F equals ma. Because if we rearrange both of those, in fact, you know what, I might write this out again. F equals ma. For this specific situation, what we're talking about here is weight. So the force that we're talking about is weight, is equal to mass, and the acceleration that we're talking about is acceleration due to gravity. So this is just like a special version of F equals ma, and that's what I've been trying to show you here. In both of these, we have rearranged to make the acceleration for that particular thing be the subject. So in this one A and in this one G, just to show you that the two things are equal to each other. So even though over here we had said like the units of G are newtons per kilogram, the newtons of G can also be meters per second squared, because it is an acceleration, and hopefully that's clear from that, like G is equal to an acceleration. So we've got a couple of questions here to do as examples before you get stuck into some questions. So let's have a little look at them. Oh, I've dropped my pen. Right, Charlie's hamster has a mass of 700 grams. I'm going to make my list of information here. Do you remember what I said about the mass in this equation? It can't be in grams, it has to be in kilograms. So we're going to have to change that. So 700 grams is 0.7 kilograms. And we have to calculate his weight on Earth. So on Earth, G is 10 newtons per kilogram. So W equals mg. Mass 0.7, gravity 10. And we get 7 newtons. On the moon, mass is still 0.7. G, it told us on that previous page there, do you remember? 1.6. And we have to calculate the weight. So 0.7 multiplied by 1.6. Oh. 1.12. Okay, now let's have a wee look at the questions that you're going to do. So I want you to do the questions on page 197. I think these two are straightforward enough. And then the questions on 198. Oh, I like wee questions like this. Oh, a bag of flour weighs 1 kilogram. What's wrong with that? Then we've got a wee table here where you've been given the mass in grams. Just make sure you convert that to kilograms before you get the weight. And I've left space here for your working out. Same here, question 4. For this part, A, B and C, you've been given the mass of objects and you have to find the weight on Earth. Whereas D, E and F, you've been given the weight and you have to work backwards and find the mass. So let's just make sure that we can do that. I've lost my page. So if I look back at this equation here, if I was to rearrange this to make mass be the subject, I would have to divide both sides of the equation by G. So I'm going to get weight divided by gravity. So that's what you'll end up using for that one. And then I'm pretty sure question 5 is very similar. It's just on the moon as opposed to Earth, so G is different there. Just make sure you're showing all your working out, please. Remember, there's always marks for that. Okay, told you it'd be a wee short one. That is me for today. I will see you next day. Bye.